Welcome back. We have here another very important question, and that is what would be the expected AC output of a 150 kilowatt DC solar PV system with 11% system losses at STC and 96% inverter efficiency? Please try to solve this. You may like to pause the video and then come back. Okay, I hope you have tried to solve this question and have come up with your best answer. Let's see how to solve this question. Here we have a couple of important data, and that is, the first one is that it is 150 kilowatt DC solar PV system and it is at STC. So we are receiving 1000 watt per meter square of solar radiation. Beside this, the data in the question is 11% system losses and we have 96% efficient inverter. Okay, let's see first what are system losses. We can have a couple of system losses and this may go up to a very critical numbers such as shown here, 22.8%. This means that we may be losing more than 20% power of the rated DC power we have installed at the site. What could be the various factors in the losses? Let's see here. First one, we have reflection losses. Reflection losses are those losses in which the air radiation when received at the solar panel front side, then part of the irradiance is not taken by the or absorbed by the solar PV cells. In fact, it is due to the fact that the solar irradiance is reflected from the glass of the PV module. So these reflection losses sometimes are very significant due to the circumstances prevailing at site, and we need to cater this during the design stage. These reflection losses may also be due to the typical or inherent structural design of the solar cells which have been integrated into the module. Number two, here we have spectral losses. Spectral losses account for those in which the spectrum of the sun irradiation received is not ideal or it doesn't correspond to that 1000 watt per meter square for which it has been calculated for. In other words, the spectrum can change its characteristics in such a way that the total amount of inherent energy is not same as 1000 watt per meter square. So the spectrum losses are also maybe significant, but normally they can be taken at low as possible, like 1% or 2%. The third one comes the irradiation losses. This is straightforward the amount or the quantity of the irradiation being received by the system. So we can assume that due to some reasons or the environmental reasons, the radiation is not at 1000 watt per meter square and it is low than that. Then comes the thermal losses. Thermal losses refer to the heating up of the solar PV module. You know the efficiency of the module decreases with the increase of its temperature. So when the solar cells are working, they are receiving the solar radiation, they start heating up and this decreases their efficiency, so they will produce less power. So we have to account for such losses. Then comes the array mismatch. Array mismatch is those losses in which when you install a lot of PV modules, then there is a possibility that the PV module may have some manufacturing differences between the two. And due to that, we know that if they are connected in series, then the current produced by the minimum current produced by one of the module is the actually array current. So due to this mismatch, we may account for the losses, because if one of the module is not producing as much current as others, then the potential is being lost here due to this particular losses. So comes the DC cable losses. DC cable losses is the losses of voltage drop between the solar PV modules and up to the other parts of the system or components of the system, which may be charge controller or the inverter. So the DC cable is a significant part, and if it is very long, like if you are installing the solar PV system at top of some commercial building or some at top of the residential, then the length may be very significant and there would be voltage drops, and they definitely be counted for the losses. Obviously, this has to be calculated in terms of the voltage drop. Then comes the inverter losses. Inverter losses are basically its efficiency. It converts the DC power into the AC power. So obviously no machine is 100% in this universe. So normally we have 95, 96, 97% inverters available in the market. But typically we can take that there will be a 44% loss or 96% efficiency of inverter is available. Then come the AC cable loss. Which one is the AC cable? The AC cable is the one which is installed at the output of the inverter. From inverter, it goes to the load or to the grid. Obviously, the voltage received at the load is actual corresponds to the power received. If the AC cable is not good, we will have drops, AC voltage drops there, and this will account for some losses. But normally it can be kept low. So we, generally speaking, we can say that it's not more than 0.5 or 1%, because the AC voltage is at 22 or 120 volt AC, and normally if the solar PV system is being installed at a residential or commercial building, so such counts have already been counted for in the design of the electrical wiring for that particular building. Then come the shading losses. We may have shading during the operation of the solar PV system, not only during the operation, but during the design phase, we have also to see the shading effect. If there is any obstacle or any like tree or some building which may come during the whole year, which can shade some part of the PV module or PV array, then definitely this is a big loss. And if you remember from some of our questions, that shading one cell or one module can significantly reduce the power produced by the solar PV module array. Comes the dust and dirt. If you have dust and dirt top of the solar PV modules, the irradiance being received by the solar module obviously is low, and we will have less power produced. So such losses need also to be accounted for. Okay, coming back to our question, let's try to solve it. Here we can see that we have number one, 150 kilowatt of DC power. Number two, we have 11% system losses. And number three, 96% of efficiency of inverter. Now, in such question, generally when question states that there are 11% system losses and at the same time the efficiency of the inverter is given, then remember that the 11% system losses do not include the losses of the inverter. So here what we have to do is, let's take the 150 kilowatt of the system. We have to multiply it with what? We have to multiply the system losses. So the system efficiency is actually, what we'll do here, 100 minus 11%, or can divide it by 100. Let's remove the percent. So here we have the efficiency of the system, or the losses of the system. And then we come to the inverter, where we have 96%. So we can take this as 96 over 100. So this comes out to be 150 into 89 over 100. Sorry, 96 divided by 100. And this becomes 150 into 0.89 into 0.96. And this is equal to 128.16 kilowatt. So the power produced shall be 128.16 kilowatt under the specific data given in the question. So our best answer is 128 kilowatt, and the rest of the data is not valid. So answer is choice B, 128 kilowatt.